We are diving into research reporting today, and I am sure some of you are already calculating how many energy drinks you're going to need to stay conscious. But here's a radical thought. Pay attention. This isn't just academic busy work designed to torture undergraduate souls, though it certainly accomplishes that as a pleasant side effect. You're going to be reading research reports in this class, which means you need to know what you're looking at when someone hands you a 20-page document full of statistical jargon and conclusions that may or may not be worth the paper they're printed on. More importantly, you're going to be writing these reports yourself, and I prefer not to grade papers that read like they were written by caffeinated monkeys with access to thesaurus. Really pay attention to this. This is important stuff. Research reports exist because scientists, despite all of their impressive educational credentials, they haven't evolved telepathy, right? Shocking revelation. But without a standardized format, academic communication would resemble a game of telephone played by people who speak, different dialects of nerd. The result would be chaos, right? Entertaining chaos, but still chaos. So here's what separates the competent researchers from the amateurs. A research report isn't just a glorified spreadsheet. Any undergraduate with basic computer literacy can put numbers on page and call it an analysis. A proper research report explains how your findings contribute to the vast web of human knowledge. Notice I said contribute, not revolutionize. Most of you aren't going to overturn centuries of established science with your first undergraduate project. So manage your expectations accordingly. It's okay to be normal and just do a normal research project. You don't have to be an overachiever, okay? Don't freak out and feel like you have to overachieve. So look at this magnificent tree of knowledge. It's like a family tree, except instead of documenting questionable marriage choices, it maps how different fields of study interconnect. We've got culture at the roots, human consciousness branching upward, life sciences spreading out, and the physical sciences reaching towards the theoretical heavens. It's poetry in organizational chart form. But this spectrum diagram, okay, even more revealing. It shows us the hierarchy of sciences. From the soft sciences, studying human behavior, and yes, soft science, I used air quotes, down to the hard sciences, where physicists argue about particles they need billion-dollar machines to detect. Social science occupies the top tier, trying to make sense of why humans consistently make irrational decisions despite having access to all of recorded history as a cautionary tale. Then we have psychology, that's us, bridging the gap between why do people act insane and what's actually malfunctioning in their neural wiring. We're sort of the diagnosticians of human behavior, except our patients lie more and the symptoms are harder to measure. So below us, we have biology, where they dissect things and pretend that life isn't mysteriously complex. Then chemistry, where they blow things up and control environments. And finally, physics, where they argue about theoretical particles and mathematical equations that may or may not correspond to actual reality. It's like a hierarchy of increasing precision and decreasing relevance to daily human experience. So here's the crucial insight that most people conveniently ignore. Science represents our understanding at a specific point in time. It's not divinely revealed truth, carved into stone tablets. It's our best current approximation of reality. Given our current tools, methods, our current level of ignorance, tomorrow we might discover that everything we thought we knew was embarrassingly wrong. And this has happened. It happens regularly, and it kind of keeps things interesting. So science is a snapshot. It's not a movie, right? We capture what we can observe and measure right now with current technology, current theoretical frameworks. Future scientists will look back at our work the same way we look back at medieval medicine, with sort of this mixture of respect for the amount of effort they went into and then just horror at the methods, okay? So a research report follows a certain structure. You got your title page, abstract, introduction, method section, results, discussion, references, and possibly an appendix if you're feeling particularly masochistic. So think of research paper as an hourglass, not because time is running out, though it might feel like that by the end of the semester, but the shape represents information flow. You start broad with your introduction, establishing context, reviewing what everyone else has discovered, and then you narrow down through your method section, focusing on your specific approach. The results section is the narrowest point. These are the precise findings from your particular study. And finally, you expand back out into the discussion, explaining what your specific results mean for the broader field. So this isn't just arbitrary academic sadism, though it certainly serves as that function. The structure forces logical thinking. You begin with the big picture, zoom in on your specific contribution, then zoom back out to show how your work fits into the larger scientific conversation. It's kind of like surgery. You need to understand the whole patient before you make your incision, focus intensely on that specific procedure, and then consider how your intervention will affect their future health and well-being. So the funnel metaphor works even better. Should I have in here somewhere, I thought. Maybe not. Okay. So you've got your background information, you filter it through your specific research question methodology, extract the results, then interpret those findings in the context of existing knowledge, and look at, are your results consistent? Do they suggest that everyone before you was right or wrong? Both outcomes are valuable, though one might be more career-threatening than the other. So if we deconstruct the components, right? So you've got your title page. The title page is deceptively simple. You've got your study title and your name. But like most things that appear simple, it's actually more complex if you want to do it properly. So your title needs to accomplish several things simultaneously. It needs to inform potential readers about your variables. You may hint at your findings, suggest your methodology, and it should remain concise enough to fit on a single line. It's like writing a haiku about statistics, right? It's harder than it looks. So here's where academic writing gets at least mildly entertaining. Research titles can be creative. So one classic example, there was a two-part study titled Of Mice, and then the second part was Of Men. Okay, literary reference. Another gem, the unsuccessful self-treatment of a case of writer's block. Okay, so some humor there. Miracles do happen in science. But don't prioritize cleverness over clarity. Okay, your title should include your key variables. It should hint at your research question. If you're investigating the relationship between student credit loads and sleep duration, both variables should appear in your title. Otherwise, you're just being mysterious, and mystery is the enemy of scientific communication. Good titles are specific enough to attract, interested readers. But broad enough to avoid boring everyone else to death. It's a delicate balance. So then we have the abstract, which is not required by APA nowadays for students, but though some journals do still require it. So the abstract is like your research paper's dating profile. It needs to be appealing, needs to be accurate, needs to be concise. Unlike actual dating profiles, however, honesty is not optional. It should be roughly 150 to 250 words, a summary, and it determines whether anyone wants to date your paper, whether they bother reading the entire paper or not, whether it's worth their time. So write your abstract last after you've completed everything else. I know this seems counterintuitive since it appears first in the paper, but you can't summarize what you haven't written yet. It's like trying to figure out your therapy patient before taking their history. Okay, it's possible, but it's not advisable. So the standard formula: one sentence from each major section, background from your introduction, key methodology from your method section, your primary findings from your results, and a main conclusion from your discussion. This isn't creativity time, it's compression time, okay, narrowing it down. You're creating the concentrated essence of your research. A good abstract allows researchers to determine whether your study is relevant to their interests without having to wade through 20 pages of reading. So it's like triage on potential readers, helping them decide whether your paper deserves their limited attention, their limited time. Okay. Bad abstracts are vague, overly technical, misleading. Good abstracts are clear, specific, honest about their findings, their limitations even. Great abstracts make readers more excited to read, to learn more. So aim for good, settle for adequate, avoid bad. Okay. So the introduction is where you demonstrate what you've actually read, that you've actually read other people's research instead of just making things up. It's your longest section because you're doing several complex tasks simultaneously. You're reviewing existing literature, you're identifying gaps in current knowledge, establishing the importance of your research question, and basically setting up your specific hypothesis. So think of the introduction as prosecuting a case. You're arguing that your research question deserves investigation, that your approach is sound, and that your study will contribute something meaningful to all of the existing knowledge. So unlike actual prosecution, however, you want to present a balanced view of the evidence. Okay, so start broadly with your general topic area. If you're studying academic stress, begin with what we know about stress in general, then narrow it down to academic context. Since we're doing, student population, focus on your specific population and variables. It's like zooming in with a camera. You establish the wide shot before moving to close-ups. Literature review is not just summarizing other studies, though that's part of it. You're synthesizing information, identifying patterns, noting contradictions, highlighting areas where more research is needed. You're telling the story of what scientists have already discovered, and basically where the story leads to next, which is your hypothesis. So you cite liberally but strategically. Every claim needs support, but you don't need to cite like 17 studies to establish that stress affects academic performance. Choose your sources based on quality, relevance, recency, peer-reviewed journals for sure, okay, not blog posts. So end your introduction with your specific hypothesis, not a vague research question, but a precise and testable prediction, such as we hypothesize that students taking more than 15 credit hours will report significantly less sleep than students taking 12 or fewer credit hours. Specifically, keep it specific, keep it measurable, keep it falsifiable. It's the holy trinity of a good hypothesis. The methods section is where you prove you're conducting actual research instead of just making educated guesses. Every detail matters because science depends on replication. Another researcher should be able to read your methods and reproduce your study exactly. If they can't, you failed at scientific communication. So divide this section into subsections: participants, materials, procedure. Each serves a specific function in the replication recipe, okay? So your participants, who did you study, how many people, what were their demographic characteristics, how did you recruit them, why did you choose this particular population? If you studied college students because they were convenient and accessible, just say that, okay, which is what we're doing. Don't pretend you selected them for some profound theoretical reasons unless you did. Okay? Be specific about inclusion and exclusion criteria. Did you exclude people who were taking medications that might affect sleep, students who are working more than 20 hours per week, international students who might be dealing with additional stressors? These decisions matter for interpreting your results and being able to replicate it later on. Make sure you report response rates honestly. If you sent surveys to like 500 students and only 73 responded, that's important information. Low response rates suggest potential bias. Maybe only highly motivated or particularly stressed students bothered responding. For the materials, this is part of the methods section. What tools did you use? If you created a survey, describe it in detail. How many questions? What type of response scales? Did you pilot test it? Include sample questions if they're not proprietary, meaning copyrighted and owned. If you used established instruments, which you probably won't be doing in this class, but cite them properly and report reliability statistics, such as we use the Perceived Stress Scale by Cohen 1983, which has demonstrated good internal consistency in college populations. Show that you choose your tools thoughtfully and not randomly. Procedure, which will also be part of methods. Walk through exactly what participants experienced from start to finish. Did they complete surveys online or on paper? How long did it take? Were there any special instructions? Did you offer any incentives for participation? Which I'm going to. I'll offer extra credit to my students for participating. Include details that might affect your results. If you collected data during finals week, that's relevant. If your survey was available for 3 weeks, but most responses came in the first 2 days, note that pattern. Think of the procedure section as writing instructions for someone with no context and questionable attention to detail. If you can't replicate your own study from your method section, neither can anyone else. Can your grandma replicate your study from just reading your paper? Okay. Then we have the results section. So the results section is where you channel your inner court reporter, record what happened without interpretation, present your data clearly, completely, resist the urge to explain what it all means. That comes later, and patience is a virtue in academic writing. So start with descriptive statistics. What did your sample look like? The mean, standard, deviations, ranges, frequencies. Give readers a clear picture of your data before moving to inferential tests. So if you studied 150 students and 127 were female, that's important contextual information. Okay? Present your analysis in logical order. usually following the sequence of your hypotheses. If you predicted that credit load would correlate with sleep duration, report that correlation first before moving to any secondary analyses. Use tables and figures strategically. A well-designed graph can communicate complex patterns, and it should communicate complex patterns more effectively than paragraphs of text. But don't just dump every possible chart into your paper. Again, it's about clarity. Choose visualizations that clarify rather than confuse. And report statistics completely. Don't just say that the correlation was significant. Give the actual correlation coefficient, sample size, p-value. Credit load was significantly negatively correlated with sleep duration. R of 148 equals negative 0.34 correlation. P value is less than 0.01. So complete reporting allows the readers to interpret the effect sizes and not just the significance. So be honest about unexpected findings. If your hypothesis wasn't supported, say so clearly. If you discover something surprising in your analysis, report it, but acknowledge that it wasn't part of your original plan. Science advances through honest reporting, although it can sometimes be difficult to get published with a negative hypothesis like that. But avoid the temptation to interpret your results in this section. Okay, students taking more credit slept fewer hours is appropriate, but saying like this suggests that academic workload creates stress that interferes with healthy sleep patterns, that belongs in the discussion section, which is what we're going over next. So the discussion is your payoff section, where all that restraint in the results section finally pays off. Now you get to interpret, speculate, theorize, explain what your findings actually mean for psychological science, for human understanding in general. So start by clearly stating whether your hypotheses were supported. Don't make readers guess or dig through statistical jargon to figure out your main findings. Such as predicted, students taking higher credit loads reported significantly less sleep, supporting our hypothesis that academic workload affects sleep duration. Connect your findings to existing research. Do your results align with previous studies on academic stress and sleep? Do they contradict established findings? If so, why might that be? Maybe your sample was different, your measures were more precise, maybe previous research missed important variables. Why is there a difference there? Discuss practical implications. If credit load affects sleep, what does that mean for academic advisors, students planning their schedules, or university policies about maximum course loads? Good research should have real-world applications, not just theoretical significance. Try telling that to physicists. You should also address alternative explanations. So maybe the relationship between credit load and sleep isn't causal. Perhaps motivated students both take more classes and sacrifice sleep for studying. Maybe the effect is mediated by other variables like stress, time management skills, caffeine consumption. So consider these possibilities explicitly in your writing. It should also have a limitation study. Every study has limitations, and acknowledging them demonstrates scientific maturity rather than weakness. So common limitations include the sample size. Was it large enough? Sample characteristics. Were your participants representative of the population you want to generalize to? Measurement issues. Did your survey capture what you intended to measure? As well as design constraints. So like correlational studies can't establish causation. Don't just list limitations, explain how they might affect your conclusions. If you only studied students at one university, your findings might not generalize to different types of institutions. If you collected data during a particularly stressful semester, that might inflate the relationship between academic workload and sleep problems. Use limitations to suggest future research directions. So, for instance, future studies should include students from multiple institutions to assess generalizability. Or longitudinal designs could help establish causal relationships between academic workload and sleep patterns. Okay. So we also have bias. Okay. So here's something that might disturb your faith in objective scientific truth. All research is biased to some degree. I know this contradicts everything you learned in high school about the purity of the scientific method, but reality is far more complex than textbook idealizations. Bias enters research through multiple pathways. Funding sources influence which questions get studied and which results get published. Pharmaceutical companies fund studies on their own drugs. Government agencies fund research that supports their policy preferences, their political agendas. Universities encourage research that enhances their prestige or brings in more grants. Researchers themselves bring personal biases to their work, so we tend to design studies that confirm our existing beliefs. interpret ambiguous results in ways that support our hypotheses. We notice patterns that align with our theoretical preferences. This usually isn't conscious deception. It's human psychology operating in scientific contexts. So we also have publication bias. Okay, publication bias skews the literature towards positive, statistically significant results. We don't like negative hypotheses, wrong hypotheses. Journals prefer to publish studies that find something rather than studies that find nothing, even though the null results are scientifically informative. And this creates a systematic distortion in the research record. When you read research, ask critical questions. Who funded this study? What were the researchers' theoretical commitments? What incentives might have influenced the design, the analysis, the interpretation? These aren't conspiracy theories, okay? They're practical considerations for evaluating research quality. You should always be looking at these. Look for potential conflicts of interest, which it should state. If a study on the effectiveness of a particular therapy is conducted by researchers who developed and profit from that therapy, you need to approach the results with appropriate skepticism. If research on the dangers of a particular substance is funded by industries that benefit from restricting that substance, consider alternative explanations for the findings. Look for other research studies that have been done as well. Check the sample characteristics. If a study on academic stress only includes students from highly competitive private universities, the results might not apply to community college students or those at less demanding institutions. If research on sleep patterns excludes shift workers, parents of young children, people with medical conditions, the findings have limited generalizability. Okay? You could consider the historical context. Research conducted during wartime, economic crises, social upheaval. It might reflect those circumstances rather than being universal, having universal principles. Studies from decades past might reflect, cultural biases, limited technology, other things, that don't apply anymore. So there's also digital bias. Okay, I don't think I have that yet. So here's a contemporary wrinkle that your professors might not have warned you about yet. Artificial intelligence and algorithmic filtering are making human bias worse, not better. We used to have to seek out information that confirmed our existing beliefs, and now it's delivered directly to our devices without conscious effort. So, search engines, social media platforms, news aggregators, they're all using these algorithms designed to show you content you're more likely to engage with. And this means you'll see more information that aligns with your existing opinions and less information that challenges them. It's like having a personal assistant whose job is to shield you from uncomfortable truths, okay? That's not healthy. If you search for research on controversial topics, gun violence, climate change, vaccine safety, the results you see are going to be influenced by your previous search history, your geographic location, and other demographics about you. The algorithm tries to predict what you want to see and not what would give you the most accurate or complete picture. And this creates an intellectual echo chamber that's more sophisticated than anything humans have experienced before. Previous generations had to actively seek out that confirming information, and now we find it automatically, and the result is increasing polarization and decreased ability to evaluate conflicting evidence objectively. So when conducting literature reviews, use multiple search strategies and platforms. Don't rely solely on Google Scholar or a single database. Use different computers maybe, clear your search history, use incognito browsing to avoid personalized results. Seek out research from different theoretical perspectives, even if you disagree with them. And be especially wary of studies that seem too perfectly aligned with your existing beliefs. If research supports exactly what you hope to find, scrutinize it more carefully, not less. The most valuable studies often produce unexpected or even uncomfortable results. Okay, so scientific facts are rarer and less permanent than most people assume. Science is less certain than we have been taught. What we call facts are actually our current best approximations of reality, subject to revision. Okay, when better evidence emerges. Scientific knowledge is provisional. It's probabilistic rather than absolute and certain. We don't discover truth so much as we construct it, and we construct increasingly accurate models of reality that work until they don't. This isn't a bug in the scientific system, it's a feature that allows us to continually improve and refine science. So consider how many established facts from previous decades have been overturned. We used to believe stomach ulcers were caused by stress and diet until we discovered H. pylori bacteria. Continental drift was rejected by geologists until plate tectonic theory provided a mechanism, and now we believe it. Hormone replacement therapy was standard treatment until studies revealed increased health risks, and then we found out that those studies were bad, and so now we're supporting it again. So even current facts come with confidence intervals and error bars. When researchers report that a correlation is statistically significant, they're saying there's less than a 5% probability that the observed relationship occurred by chance. Not that the relationship is for sure real or that its magnitude, how powerful it is precisely known. And this uncertainty doesn't make science useless, it makes science honest about its limitations. It's not a religion, it's not a fact, okay? Scientific methods are designed to minimize error and bias, not eliminate them entirely. The goal is to be less wrong over time, not to be perfectly and immediately truthful. So when reading research, pay attention to confidence intervals, effect size, replication studies. A single study that finds a significant effect might be less convincing, and it should be less convincing, than multiple studies that find consistently moderate effects. Look for meta-analyses that combine results across studies to get more stable estimates. Okay? Be suspicious of research that claims to have definitely proven anything. It should never make those claims. Science provides evidence for and against hypotheses, but definitive proof is rare and usually temporary. The strongest scientific statements are probabilistic. Based on current evidence, X appears to be related to Y under these conditions. It appears to be. Okay? So being a critical consumer of research doesn't mean being cynical or dismissive. It means being thoughtfully skeptical, okay, and systematically evaluative. You want to extract useful information while avoiding the trap of accepting everything at face value. So start with source evaluation. Where was this research published? Peer-reviewed journals have quality control mechanisms, but they're not perfect. Be especially cautious of research published in predatory journals that prioritize profit over scientific rigor, and you'll discover this as you get better in your field. Okay, you're not going to know it now. But check the author's credentials and affiliations. Are they experts in their field? Do they have conflicts of interest? Have they published related research before? What do other scientists think of their work? You need to examine the methodology carefully as well. Was the sample size adequate for the analyses performed? Were participants recruited in a way that allows generalizations to relevant populations? Were the measures valid and reliable? Was the study design appropriate for the research question? The results section, we never look at it before the discussion section, although you should. Authors sometimes overinterpret their findings or downplay their limitations. The raw results in the results section tell you what actually happened. The discussion tells you what authors think it means, and these aren't always the same thing. Okay, sometimes you see really bad statistics in the results section. Pay attention to the effect sizes, not just the significance. A statistically significant correlation of 0.15 might not be practically meaningful, even if it's significant in the technical sense. Large sample sizes can make trivially small effects statistically significant. Consider replication and consistency across studies. Single studies, no matter how well conducted, are less convincing than patterns of findings across multiple independent investigations. So you want to look for systematic reviews, meta-analyses that synthesize evidence. Think about alternative explanations for the findings. Could the results be explained by variables the researcher didn't think about or didn't control for? Are there other interpretations that fit the data equally well? Okay? These mistakes are made all the time in science. So writing a research report is like performing surgery without words, okay? Precision matters. Every cut should be intentional. Sloppiness can be fatal to your argument. Academic writing has its own conventions, rhythms, expectations that differ from other types of communication, right? So clarity trumps cleverness.